Hi, in this video we're going over the question A2 of the 2022 USAPhO, and I need to introduce myself first. So I'm the 2022 US physics team member. I'm not in the traveling team, but I'm still like top 20, okay? So let's go over question A first. So it asked for the value of Q0. For this question, you need to know two things. The first thing is that the electric potential energy is given by this formula, which is equal to 1/2 times the summation of Qi phi I, where Qi is the charge of the ice particle, and phi I is basically the potential act on the object I by other charges. And you also need to know is that the potential energy stored is also equal to sigma times A, which is the surface tension times the area. So for example, if you have a small area A and with surface tension sigma, the energy stored is actually equal to rho times the surface. And in this case, because the case we're dealing here is a sphere, where the area is actually equal to 4 pi r squared, we have the surface tension or the surface energy to be equal to 4 pi r squared times rho or sigma, right? And secondly, we need to discuss about mass conservation. And for the problem, we know that the droplet splits evenly into two parts. And from the conservation of mass, we can have this formula over here. And solving this gives us R1, which is the radius of the sphere after the first split, is equal to 1/2 to the 1/3 power times R0, where Q1 is equal to half of big Q0. And we denote a small q as the charge on the sphere just after splitting, and big Q as the charge just before splitting happens. And now let's write the equation. So first, because the problem stated that the energy of before splitting is equal to the energy of after splitting, we just plug in what we have. And this part is the total energy of system before splitting, and this one is a total energy after splitting. There's a factor of 2 over here because there are two droplets. And by plugging in the numbers and solving all of this, we got Q0 to be equal to this stuff over here. And moving on to part B, and I accidentally wrote 2 over here. So it is asking for the value of small q n after the n split. So let's first write out what is the value of r, just using the conservation of math, and we can see that each time the r is reduced by a factor of 1/2 to the power of 1/3. So from this series, we can see that Rn is actually equal to 1/2 to the power of n divided by 3 times R0. And now let's take a look. What is the value of big Qn? So from the equation we have over here, just let me mark it. You can see that the value of Q0 is proportional to the value of R0 to the power of 3 over 2. Right. And because that is the case, we can see that Qn is actually proportional to Rn to the power of 3 over 2. And we already know Rn is equal to that. So we just can plug in the numbers and see that Qn is actually equal to Q0 times 1/2 to the n divided by 2 power. And now, what is the value of small qn? We only need to consider the case of Qn, big Qn, splitting into two smaller parts, right? From the conservation of charge, small qn is equal to Qn divided by 2. So now we can get the small qn to be equal to this. And let's move on. For the third question, we're supposed to find the total work done when the droplet splits infinitely to very, very small. Let's take a look at what actually happens. So during the first little bit, we have the uncharged ball at first, right? And then we charge it to Qn. And then the Q0 splits into Q0, two small Q0s. And then we move on to process 2, which is the small Q0 charged up to Q1. And then the Q1 splits into smaller Q1s. And we have a Q1. And then it charged again. And this process continues indefinitely. So let's figure out what is the work done. You see that because we assume in this question, we assume that the metal ball is not expanding. So we don't really need to care about the surface energy. We only need to consider the energy of electric potential energy. So for the first time, when we charge from 0 to Q0, the energy change is equal to this. And now, how about the second time? We have a small Q0 charge to big Q1. We have the energy change to be equal to this. And for the nth time, we have the equation to be this, and n plus 1's time to be this. And something to note here is that we only need to care about the change of EP of Q1 and Q0. Why? Because we only need to consider the part of the droplet that is attached to the voltage. And we don't really need to care about the droplets that is split away, because when splitting, we don't really need to care about the work. There's no work done by the current or the voltage or the source. So we don't need to care about that part. And now let's take a look at the work done on nth term. We just can plug in the equation. So for Rn, that is equal to 1/2 to the power of n divided by 3 and times R0. And because we need to reverse it up, it is equal to 2 to the power of n divided by 3. And now let's plug in the value of Qn. That is equal to this part. And squared and minus 2 to the power of n divided by 3 and times this. And this one is basically Qn minus 1 squared. And from organizing the equation, we can see this whole term simplifies to this term. And now the total work done is basically the summation of all works. This part plus this part and plus all this part. And there's something to notice is that we can break this in half. So, and when we break this part in half, this part is equal to 2 times this term. And something to notice is that when n is equal to 0 for this part is equal to 1, and this part is equal to the 1/2 of this term, right? So this whole expression can be simplified to this term plus the summation of n equal to 0 of this term. And from series, we know that the infinite summation of this is actually equal to 1 divided by 1 minus the common term, or the 1/2 to the power of 2 divided by 3. And now, when you plug in back, you can see the total work done is equal to this times rho r0 squared. And you can see that the value of b is equal to this. And that's it for this video. But I want to add something. This problem assumes the sphere cannot expand, but that is not stable. The energy is not like minimal. All right. So the correct way we do this is to assume the sphere can expand. So now let's look at the problem again. We have E is equal to all this term. And when we want to minimize this term, we just take the derivative of this term. And that is equal to 8 pi rho r0 minus q squared, 8 pi epsilon r0 squared equal to 0. And now from this equation, we can actually find the actual value of r0, which is equal to the cube root of q0 8 pi epsilon times a pi sigma. And that is the value of r when the droplet is about to split. But you can solve this problem using this method, but I tried during the actual test and failed miserably because the calculation is too long. So the premise is that USAPhO is not too difficult as it seems. So you gotta assume some conditions when doing the test. Otherwise, the problem is going to blow up.